Yes, buddy.
The 3-2 notes.
The 3-2's not out? Oh, well, holy cow. My bad. I could have sworn I pushed them out this morning. I was pushing out all my other notes. Thanks for the heads up real quick. Alright, let's see if it goes out. Progress reports for high school start coming out this Friday, so I've noticed a slowdown in Skyward because of that. Everybody trying to update grades. Alright, we should start seeing it coming into your, well, in that folder of yours is what should happen, okay? Thanks, bud, for telling me that. All right, so again, we did measure of centers on Thursday, your mean, your median, your mode. Today, we're going to focus on measures of spread. Measures of spread are typically your range, your standard deviation, your variance. There is another measure of spread. We talk about it more tomorrow in the lessons with 3-4 and 3-5. Another measure of spread is what's called the IQR, the interquartile range. So we'll define that more tomorrow. But that's another measure of spread. Then our other goal today is to talk about the empirical rule to describe data that are bell-shaped, and then to use Chebyshev's inequality to describe any set of data. So again, when we say any set, we mean also skewed, because you can only use the empirical rule when it is bell-shaped or looks approximately normal. Whereas Chebyshev's, his inequality can be done with skewed graphs. Okay, so his formula is a little bit different. So we learned a long time ago what range was. Range is basically the largest value minus the smallest value is what our range is. The challenge about range is it's a very vague description of the data. Okay, it just, if you have outliers in your data set, those outliers can really distort what the main focus of the data is around, or how and where it's at. And so a range is really not the preferred method of describing a set of data. You use it very rarely. They're going to have you go through and calculate it. So always remember, as we go to calculate it, to find the range, it's always the maximum minus the minimum. Okay, max minus the min is how we find the range. Okay, so if you the great thing again about the one var stats, when we type in the data into L1 and do a one var stat, it automatically finds the max and the min for us. Okay, now you don't have to. You could look at a table of numbers and say, hey, that looks like the smallest and that looks like the biggest, and let me subtract the two. So you don't have to type the numbers into L1 to figure it out. But since we're doing this stuff in the table for technology for so many other things, we might as well just use it to our advantage and just, hey, do the one var stats, let it tell us what those numbers are, and then subtract them. Your measures of dispersion are meant to describe how spread out the data are. In other words, they describe how far on average an observation is from the typical data value. Standard deviation is based on the deviation about the mean. So as we're going to focus mainly talking about now, the mean, the standard deviation, and variance is the next couple topics we'll talk about. There are set formulas by hand to do them by. It's pretty lengthy. The book goes through and walks you through how to do it by hand. None of the homework problems require you to do it by hand. So, we'll be able to use technology to do it, but I'll talk about how do we find these things, the standard deviations and the variance by using formulas. The little note here, the sum of all deviations about the mean must equal 0. And again, as we look at, I'm going to zoom right in here real quickly. This is basically the x sub I is each term, each data term. And again, we learned in this case on the left, the mu there, that was my population mean. And so the statement up above saying that if I take each data term, subtract the mean from it, add up all those answers, I'm supposed to get 0. That's what that little statement up above says. The sum of all deviations about the mean must equal 0. So you would take each data value, subtract the mean from it, add them all up, and I should get 0 for an answer. The other one is, again, just the x bar is my sample mean. Remember, we need to make sure we know our symbols, and that's still our data term, each data term. So it doesn't matter if you're talking about the mean, the sum of the deviations for a sample or the population, there's still the sum of the deviations must equal 0. Now, population deviation. It's represented by that lowercase sigma. That I call it fat R, is what I call it. It's a little fat R. And so basically it's a variable is the square root of the sum of all the squared deviations, all this junk here. So in a nutshell, as we see a formula down below. So in order to calculate the standard deviation by hand, you would first have to go in, find the mean of the data. Then you're going to take each data value, subtract the mean from it. You'll get an answer. Square each of those answers. Then you will add up all those squared answers. Then you're going to divide by the population. You're going to divide by the population, so the total number in your sample. And then you'll square root it. That's the process that it goes through. Okay, you find the mean, subtract each data value by the mean, square the answer to make it positive, add up all those answers, divide by your total number in your sample, square root it, boom, you got your standard deviation. Standard deviation has to be a positive number, okay, because you got to think about it. Can we take the square root of a negative? Nope. Plus, when we square all those subtraction problems and stuff, when we look in here and we subtract the mean from each data value, some may be negative. When I square it, it all becomes positive. All right, so that's why, one little note, standard deviation has to be positive. It can be anything from 0, and just keep on going. It depends on how far out spread apart your data is. Okay, the closer you are to 0 for a standard deviation, that means your data values are really close together. The bigger your standard deviation is, that means your data values are more spread out. And we're going to see that here in a little bit. Okay, so if by chance you get any nice, as you're doing the math, keep in mind, I should not get a negative for a standard deviation. It should always be a positive, okay? Again, I define what those little things are there. The sample deviation, same look of a formula. The only difference is we're dividing by n minus 1. So in the population, you're dividing by your total sample size, or whatever the whole population as a number is, whereas your sample deviation, you're dividing by your sample minus 1. The reason why we do the minus 1, some books will talk about there is give a little bit of room for error because we don't know the true population when we work with the sample. So we divide by, since there's one variable we're working with, we do n minus 1 to divide by, just to give it a little bit more room. Your sample deviation, we'll see it on the screen with the 1var stats at the same time with the population standard deviation. It calculates both of them for us in an instant. And the sample deviation is going to be a little bit bigger than the population. Not drastically bigger, just a little bit bigger. And it just gives a little bit more room or wiggle room as we're trying to infer to the greater population when we're working with a sample. Okay? So if you're doing this by hand, those are the two formulas that you have to kind of follow, whether you're doing the standard deviation of the population or the mean or the sample. Again, we're going to mainly focus on doing technology just to make our lives easier, speed it up with the process. Okay? Because if you're dealing with, as we saw last Thursday, and we worked with the M&M's problem and another problem, they had like 30 or 40 things in the sample size. That would be a pain in the butt to find the standard deviation by hand, where you got to find the mean, take each data value, subtract it by the mean, get 50 different answers, square each of those answers, then add them all up, then divide by whatever, and then square root it. That's just a heck of a lot of work if you have a lot in your sample. And that's where the technology helps. If you're working with 5 numbers in your sample, heck of a lot easier to do it by hand. Okay? So When we're doing this, again, I put a little note in here. We're going to enter our data into our table, into L1 or L2, whatever you want to do in the calculator. I did put a link on one of the pages for tech thing where if you want to do it in some of those other online programs like Ministat and those different programs, you can do it there. I would say just stick focus with the TI-84 because that would be the easiest for test day. So we enter the data into the table, we choose one var stat, and then we make sure that we make sure the correct column that we're doing the data on is what we've chosen. And then I put a little note that S sub X is the sample deviation and little fat Rx is the population standard deviation. When we go to interpret the standard deviation, we talk about it representing the typical deviation from the mean. So we'll talk about the data typically varies from the mean by a certain amount, is what we end up describing it. Again, this is where I made a little note in here before that. If standard deviation, I'm going to just abbreviate standard dev, closer to 0, then data not spread out as much, and it is closer to the mean. Again, standard deviation, is a description of how far the typical data is away from the mean. The smaller the standard deviation, the closer you are to 1, that means that your data values are hugging the mean. They're really close to the mean. The more spread out the data is, so when the standard deviation is farther away from 0, okay, that means your data is more spread out. We could have standard deviations of 3 and 5. We could have a standard deviation of 20. Just depends on how spread out the data is. And that's where some of those outliers affect what's going on. So we'll make a note about that there as well. So another note about standard bigger standard deviations mean the data is very spread out and away from the mean. And there's times when we look at, sometimes we're not given the data numbers, we're given a picture, a dot plot, or a histogram, and then they ask us a question of, well, which data set here has the smallest standard deviation? Which one has the biggest standard deviation? And they don't give us any numbers. They just show us pictures. Well, if I notice that, if it's bell-shaped, then if there's a lot of data in the center around where the mean would be and very few outlier numbers, then I can say that, hey, that's got the smaller deviation compared to something that has low frequency in the middle and a lot of frequency on the outside away from the data. Okay? And so we'll have some examples of those pop up as we get ready to do some problems. And I have our first example coming in here. And again, here's some terminology. I've talked about it a couple times. The larger the standard deviation, the greater the dispersion or spread. That's kind of what I've been talking about up above there. We always refer to stuff back to the mean. Okay, we don't say the standard deviation is related to the median. It's always related to the mean, is what it's referring back to. How far the typical data values are away from the mean. Now, here's our little example. In the exam scores down below here, I got them listed below in the table. It says the following data represents exam scores at a statistics class taught using traditional lecture, like what I'm doing right now, and also doing the flipped classroom where you watch a video the night before come in, and then all we do is practice in class and do that technique, okay? The flipped class is one where we did it. So which course has more dispersion in the entrance scores using the range as the measure of dispersion? So here we're going to do traditional. We're going to find the traditional range, and then we're going to find the flipped class. What is the range for that one? So looking at traditional, is 56.2 the smallest? Trying to do a quick eyeball. That looks like the smallest. And so that looks like the smallest. That's the min. And is 85.3 the max? Anybody disagree with me on the traditional there? All right, so 85.3 minus 56.2 equals 1 point, borrow, that's a 29.1. Hopefully I borrowed right. So there's my range for the traditional classroom. It has a range of 29.1 points. And then for the flipped classroom, its range, as I go down here, looks like 63.4 is my min. Looks like 91.8 is my max. So 91.8 minus 63.4. That would give me 0.4 borrow. That's now an 8. So 2. That's now an 11. 8. 28.4. And then they would say, okay, which method has a greater range of dispersion or more dispersion? And we would come in here and say, well, the traditional class, the traditional class has greater dispersion. Again, it's not by much, but technically it's bigger. 29.1 is bigger than 28.4. And so technically it has greater dispersion among it. But as we were looking at some of those numbers, some of them were pretty close to each other. So that's where we would say, okay, let's take a step back. Let's look at standard deviation. Does that give us a better picture? Okay. When I looked at the flipped classroom, there was only one number in the 60s, and then it jumped up into the 70s and above there, and a couple in the 90s, whereas the traditional had the 56, and it had one in the 60s, or a couple in the 60s. And so that's where we'll go, and we'll say, okay, let's go ahead and put these, and I'm going to do the traditional in L1, and the flipped in L2 is what I'm going to go through and do on the calculator right now. So I have not preloaded this, so this is going to take me a moment to get it in there. So this will give you time to put those in as well. So we're going to go stat, hit enter on edit, and then carefully type in what you have. Remember, careful on the happy fingers. We can really change or alter the outcome by just being careless in what we're typing in. All right, it looks like I got everything in there. So you 2, 4, 6, 8, 10, 12, 13. Yes, I'm on line 14. I'm going to go ahead and enter in L2 to set the other column while I'm here, just to make life easier. Mr. Stevens. All right, looks like I got both of those set up there. All right, so now that I have those in the columns, now I'm going to do a one var stat on each column one at a time. Okay, then again I'm going to go after looking for the population. It doesn't matter in this one. They didn't specify which standard deviation we can use, so it's okay to use the population deviation here. So I'm going to hit stat, go to calculate, hit enter on one var stat. It's already primed to do it on L1. I'm going to go down and hit calculate, and here we go. So for the traditional, the little fat RX is 8.4899 as we look at rounding. The S sub X, just to point it out, the sample deviation was 8.8366. Notice it's just a little bit bigger, okay, because it divided by n minus 1, it divided by a bigger number is why it's a little bit bigger. Now, as I looked at the flip class, I got to go back and do another one var stat here. So as I look at the fat RX and the SX for that one, so stat, calculate, one var stat, change it to column 2, so second 2 changes it to column 2. And then on this one, it was 7.54207, and then it was 7.8500. So now, as I've gotten the standard deviations, whether they wanted me to do population or sample, really didn't matter. In both cases, the traditional was larger, okay? Instead of being, when we looked at the range, there was about a 0.7 difference between the two. Now I'm seeing it as it being, there's a, let me make sure I look at my eyeballs right here. Yeah, there's a 0.9 on the population, and there's about a 1 point on the sample deviation. So there is a little bit greater variance there, but we would still say the same thing. We would say that the traditional classroom has greater dispersion. Again, it doesn't matter which version of the standard deviations we look at, it was still bigger. Okay, so that means the data was more spread out. They asked us to suppose the score of the 59.8 in the traditional course was incorrectly recorded, so you had happy fingers typing it in, and you put in 598. How does this affect the range? How does it affect the standard deviation? So this one we can think about as the range part. My maximum would have been 598, and then what would have been my new min for the traditional? So the new min would have been, or the min would have still been 562. So if I subtracted those two, there's what my new range is for the traditional. We went from having a 29.1 spread to a 541.8. So it made the range be a lot larger than what it should be by having a keyed in error. The question now we think about, is it going to do the same thing to the standard deviation? Will it make it be a lot larger than what it should be? Again, all we have to do is go in here and just go back to our table, and we can say, all right, let me find that in the table 1. Let me find that 59.8, which was the last number. And I changed that to be 598. Do another one var stat on that column. And we find out that the standard deviation now is, whether it's the fat RX is 140.1596 or the sample deviation is 145 0.8828. So having a keyed in error really changed what both of those were, okay? And that's why we got to be so careful entering data, because a lot of times we just trust what technology gives us, and we should at sometimes take a step back and say, hey, all these numbers were double-digit numbers. And if I'm thinking about the range, when I'm subtracting two double-digit numbers, I should get it maybe a single-digit or a double-digit answer. Whereas on this case, subtracting a triple-digit and a double-digit, I got a triple-digit answer. So we should use some of our little common sense to say, hey, all these numbers were in the 50s to 90s. I shouldn't be getting something of a range that's way bigger than what my stuff is. And then the standard deviation, a little bit harder to do that with, but again, if the data values are not that spread apart, it shouldn't be a drastically huge number, okay? Here we can see what the extreme values can do, an outlier can do to the data, whether it's the range or the standard deviation. And we talked about this terminology on Thursday, that the median was resistant to outliers. The mean was not. So now we can group the standard deviation and the range as being not resistant to outliers or extreme values as well, is what we can group into that. All right, so next one here. It's almost fishing season. So Ethan and Drew went on a 10-day fishing trip. The number of smallmouth bass caught and released by the two boys each day was as follows. Find the population mean and the range for the number of smallmouth bass caught per day for each fisherman. Do these values indicate any differences between the two fishermen's catches per day? Explain. And then we have to draw a little dot plot for each one here. And then which fisherman seems more consistent? What would we think about more consistent would be if we're looking at a picture? What would you guys think more consistent means? Looking at a dot plot. What would be more consistent in your mind? All right. Ollie, you're saying flat, okay? Uniform is what that is. We learned that term earlier with some of the stuff we're doing. What's another thing we can do? Because as we look at our dot plots, is there a frequency of one of those terms occurring more often? Okay. So being more consistent could be, maybe catching the same number of fish or around the same amount multiple times. So, and on this one, they're wanting us to think about consistent not as being uniform, flat across, always catching, one set amount. It's actually, okay, what is the mean? Which one of the data values doesn't have it spread out as much? So there's more data around the mean, which means the standard deviation is going to be smaller. Okay, that's what they're asking us to kind of think about this one. So do me a favor, type in those two guys into your L1 and L2. Find the mean, you're going to have to go ahead and find the standard deviations too for the third part. So I'm going to catch up and do it on the screen as well. And again, if you just want to copy down what I'm writing down for numbers, that's fine. But we should get practice putting it in there. Remember, we arrow up to the column header, hit clear, arrow back down, it clears it out. So I'm putting the Ethan in L1 and Drew in L2. All right, let's see. All right, going over to the other one. And then we go 15, 2, 3, 18, 21, 17, 2, 19, 3. There we go. All right, so I got my data in there. They want us to do a dot plot as well. It's going to be a crazy looking dot plot. 5, 10, 15, 20, 25. True. 5, 10, 15, 20, 25. All right. All right, let's do our one var stats here. All right, so for Ethan, the mean is 10. Grabbing his Ethan standard deviation. I'm just going to write down the population because we did have his whole sample of fish for the 10 days. So that's why we can validate saying, hey, his total population was this. So 4.8580. And then the range. I'm going to scroll down on my screen here, and I'm going to see what the min and the max are. They said my range would be 24 minus 5, which is 19. And then now we can go over and find Drew. So stat, calculate, change it to L2. Oh, he had the same mean. His standard deviation for Drew was 7.9120. All right. What is his range? His range was 20 minus 1, which is 19. So they had the... all right, that's all I need the calculator for. So they had the same mean. They have the same range. Okay, so saying who's a better fisherman based on the average cost or average caught and the range of the so forth, their biggest amount minus smallest amount. Right now they look like they're tied. So now we're supposed to look like, okay, let's look at the dot plot. Again, this one takes a little bit of time to do. And again, I didn't use going by ones on the scale here, so there's some approximation here. I see the number 9 for Ethan 1, 2, 3 times. So 1, 2, 3. Then he has 1, 2, 3 eighths. 1, 2, 3 eighths. He has 1, 2, 2 tens. So right there. He had a 5 once. And then that got rid of that one. And then he had 24. So somewhere over here. All right. So there's Ethan's little dot plot. Then I go over to Drew. And we start doing with Drew here. He had a 1. So way down here, 1. He had a 2, 1, 2 times. He then had a 3, 1, 2 times. And then we start having some big numbers. He had a 15. He had a 15, a 17, an 18, a 19, and a 20. And so, from the first one here, when we talk about the difference between the two catches, right now on the first part, I would say there's no difference. There's no difference when comparing mean and range because they are the same for both fishermen. Now looking at the picture, when we think about consistent, which means they're catching about the same amount each time. Here's a little interpretation. I'm sure some of you will say, Ethan, here he has a lot of consistent catching here. He's consistently catching anything from 5 to 10. He has multiple catches in that range there. And then we look at Drew. Well, Drew's got a lot of spread out here. There's a lot of spread when we look at this gap in here. There's a huge gap here. And then this is where we got to be careful. We can say, well, he did consistently on these other days catch in the teens each time. And on the other half of the days, he consistently caught very few fish. So he was either very consistent on catching very few or catching a lot. Okay, and then that's where so with Drew, we'd have to say that, hey, he's either struck gold or he didn't get struck gold. He had a lot of bad days there, but he also had some good days. Okay, to me, I think Ethan's more of a consistent fisherman because he pretty much caught everything around the same amount except for one high day. And so that's where we'd have some interpretation there, and you'd have to explain why you think which one is more consistent. I think this gap separates who's the better fisherman. I think Ethan's the better one in that standpoint. When you're looking at consistency, we can figure out who caught the most fish because that's what my kids do when we go to Canada every summer. We kind of have a little fishing derby, and I take my kids up to we have a cottage on a lake, but there's another lake where we have to hike up a hill, go across a railroad track, and nobody's on that lake. So it's no houses whatsoever. And so we go up there and we fish. And my daughters and my sons it's basically, I take them up one at a time, and we fish all day, and it's a competition to see who can catch the most fish, getting up there at 6:30 in the morning, coming back by lunchtime. And my daughters kick my son's butts every single time and stuff. There was one day both daughters caught 30 smallmouth bass on back-to-back days, and the boys caught like 12 to 15 when I took them and stuff. So my daughters are very competitive with fishing and stuff. So they don't like getting skunked when they go out fishing and stuff. So we found the population deviation and Here, this brings it back to why I think Ethan is a more consistent fisherman. Ethan has less spread. There is less variance or spread. Sorry about spelling that one wrong there. There's less variance or spread with Ethan's data. Here we have greater variability with Drew. And again, to me, range is very limited. We can't use the range to describe much that's talking about because it's vague. It's just, hey, biggest minus the smallest. It doesn't give you a good picture, whereas the standard deviation gives us a better picture of, hey, Ethan is more consistent. He has less spread, so he is more consistent in his fishing abilities. Okay? Maybe it's based on, hey, he's picking the right areas to fish with, right lures to fish with, technique for catching them compared to, what Drew's doing. Drew maybe just got lucky, and got those big days, and he got lucky on one day and said, oh, let me try this place again, and got lucky again. So, whereas it looked like Drew was more consistent on what he was doing. Here's an example. Again, I'll leave that one if you want to do it a little bit later. For you to put in there and make a decision on who's got a smaller standard deviation, which one would you buy. If we get some more time, we'll come back to this one in the lesson, just because it's going to take us some time to get through some of that. So we'll come back to that one if we get a little bit more time later. Now, variance. How do you find the variance of a variable? Well, the variance is the square of the standard deviation. Okay? I wrote the symbols for what variance is. The population variance. Population variance has basically the little fat R squared. The sample variance is, basically your S sub X squared. Sometimes we'll see it as an S squared. All right, now our calculator does not give it to us on a 1-var stat. It does not display it for us, okay? So the variance is something that you're going to have to do by hand, is what you're going to have to do by hand. So when we're using technology, when I find out that my standard deviation, let's say, is 5.1, I find out that my standard deviation is 5.1. And they ask me for, well, what is this variance? What is R squared? Then that's when we have to go to the calculator and say, okay, what is 5.1 squared is what I have to go through and do. I have to take the physical variance or the standard deviation and square it in the calculator in order for me to get it. Okay? Now, when you're doing these for homework problems, make sure you use all the decimals. When we do a test, make sure you use all the decimals for the standard deviation, because we don't round until the last calculation is done. So once you do a 1-var stat, we want to take a bunch of those numbers, put them in there and square it. And then we can round to the 4th decimal or the 3rd decimal, whatever they tell us to. Okay? Now, if they flat out tell you that the standard deviation like I did is 5.1, then you can just go ahead and type it in that way. But as we look at our answers from up above here, when I look at this standard deviation being 4.858, and then whatever was next, I need to use all those decimals and then square it. And then round it to whatever place value they want me to round it to. Just trying to save you some issues on doing homework problems. Same thing goes the sample variance. Once we get the SX and they tell us what it is, 1.923675, then I just square that. The variance, the standard deviation squared, is equal to whatever 1.923675 squared is. I take all those decimals and square it. Okay? There are faster ways to do it in the calculator as opposed to having to type it in. Would you like me to show you how? Let me show you how to, so you don't have to type in all the numbers. Okay. So let's go back to our TI-84 calculator. So I'm going to bring that sucker back up. So right now we've already done a 1-var stat on column L2 is what I have going in right there. All right. I have, I have my standard deviations listed up above for Drew is what I have here. So if I want to find the variance for Drew, so let me get a little clear spot here. If I want to find the variance, I'm just going to abbreviate VAR. The variance for Drew, and we know that it's got to be, and we can use the 7.9. We know we got to do 7.912016178 squared. We know we got to do that. Well, here's how we can have the calculator do it a lot easier for us so we don't have to type it in. If we press right, you see the button that says VARS, V-A-R-S? That stands for variables, is what that stands for. All right, so to the left of the clear, there's a button that says VARS. Press VARS. Then arrow to the right to actually, don't arrow to the right. Arrow down, sorry. Option number 5, statistics. And then once I arrow down to option number 5, I'm going to just press 5. Now, here's all of my statistical symbols. Now, notice that option number 3 and option number 4 are my standard deviation symbols. So I'm going to go down to option number 4, and I'm going to press enter. And then I'm going to tell it on the screen, I'm going to tell it to square it. So I got the little fat RX on there. I got the little fat RX, and I told it to square it, and I hit enter. And it's going to tell me that it's 62.6. Now, I'm going to quickly type in 7.9, 1201617.8, and then I'm going to hit squared, and I get 62.6. Once you do a 1-var stat, all of those answers for statistical stuff get stored into those variables. Okay? So if I want to find out what's the variance for Ethan, I got to go back and do a 1-var stat. So if I want to go through here and say, let me figure out what is Ethan's variance for Ethan. I'm going to go back and hit stat, calculate, enter, change it back to L1 for Ethan, go through the motions. Boom. Now that that's done, again, I can go variable, so VARS, arrow down to option 5, hit enter, go down to the same standard deviation. I'm doing population, option 4, hit enter, and then square it, and then hit enter. And this tells me that his variance is 23.6. Now, who had a greater variance? Between Drew and Ethan, Who had a greater variance? Drew. Okay? Remember, the smaller the standard deviation, the smaller the variance means the smaller the spread of the data compared to the mean. Okay? And then when we're making these decisions of stuff statistically later on in this course, we want to see, okay, what's going to help us get a better inference? So can we get our data to be closer to the mean? What effects do we need to do to cause that to happen? Maybe it's get a bigger sample size as I'm doing a study. It's be a better standard deviation that's closer to the mean, less variance and less spread out. Okay, so here, again, this variance should always be positive because of the squaring. Should always be positive. It's technically the last step before you square root in the handwritten formula, is what it technically is. The answer, once you divide by n or divide by n minus 1, that's the variance. Once you square root it, now it's the standard deviations. Okay? So again, if you have trouble doing that with the calculator, let me know. I don't mind helping you with it and getting you get familiar with it. Now here's where, as we get ready to finish up and we talk about the empirical rule in Chebyshev, as we go any further, those of you that had Algebra 2 last year got this. You might have got it the year before. Okay, at least the empirical rule. Because I think I remember teaching it 2 years ago when some of you were sophomores. I'm trying to think. I know Autumn, Audrey, I had you last year. Who did I have? Anybody in here that I had the year before? No. I think the ones of you that are in here, I had you last year. I didn't have you sophomore year. Okay. So who had Algebra 2 your sophomore year? Jackson. Okay. Did you guys remember doing the little bell-shaped curve in Algebra 2? Yeah, you remember it's vaguely there. Yeah. Yes. Yeah, there's percentages that make each quadrant. Yeah, so it's in there back. We'll pull it out real quick. And you guys might have been one of the first years we started doing it just because we knew standards were changing and stuff on there. So the empirical rule can only be used when you have your data is roughly bell-shaped. It's either is bell-shaped or roughly bell-shaped, so it's roughly symmetrical. You can only use the empirical rule for this. If your data is skewed, that's where Chebyshev comes into play. Okay? Chebyshev takes into account for everything, whether it's skewed or symmetrical. But in order to use the empirical rule, and this is a rough approximation. We get to learn later on a more exact way to find some of these probabilities or what percent of the data is within so far away from the mean. So the empirical rule states that approximately 68% of the data in a bell-shaped distribution will lie within one standard deviation of the mean. So the mean, whether you're talking about mu or x bar, is always in the center. All right, so as we go down the label this sucker down here, the mean is always in the center, whether it's mu or x bar, doesn't matter. They tell us that 68% are within one standard deviation of the mean. So that basically means one deviation to the left and one deviation to the right. 68% of the data, when it's roughly symmetrical, is within those two things there. There is approximately 95% within two deviations. So that's going another deviation each way. So that's going out here to -2 deviation to +2 deviation. 95% of the data is within two deviations of the mean. Now that means that 5% is outside. The last one here, 99.7, within three deviations, so all the way across from out to out. Three deviations, from -3 deviations to the left and 3 deviations to the right. 99.7% of the data is within 3 deviations of the mean, according to the empirical rule. Now, each of those zones has a certain percentage roughly associated with each one of them. We're going to fill in what those amounts are real quickly. As I taught it in Algebra 2, it's just a matter of memorizing as we do stuff. So starting in the middle. If the 68 is split in half, what's half of 68? Yeah, 34. So there's 34% in this zone and 30, whoops, sorry. It was just right in threes. 34% in this zone. Technically, it's a little bit bigger. It's like 30. It's technically like it's 68.1 something, but it's just say, hey, roughly 68 is just 34 in each. Now, if I think about what's the difference between 95 and 68, so what's 95 minus 68? Should be like 20. What is it, like 27? And then what's 27 divided by 2? Yeah, so there's 13.5% in each of these next zones. Now, we can do the math more. What's 99.7 minus 95? We should give it like 4.7. All right. There are 2.35%. Whoops, that's not a 5. Come on, backup tool. There we go. There is 2.35% in this last, and there's in those zones right there. Now, under a curve, 100% of the data has to be underneath. The last little spots way out to the corner are 0.15%. Not even a percent. Not even a quarter of a percent. About 1/6 of a percent, because 1/6 is 0.16666. So about 1/6 of a percent of the data are outside on each side of 3 deviations either way. Okay, so those are like your little outliers, is what those are. It's just they're out there, but it's just there's not a lot of frequency of data being there. There's greater frequency occurring around the mean, and then going out from there. We use the empirical rule to help us try to decide, well, what percent of the data is between this mark and this mark, or this zone and this zone, as we start looking at, especially like for teaching, what percent of my data is in this range, and I could, say, hey, is it a big percentage or small percentage? So here's an example. The Stanford Binet Intelligence Quotient, or IQ, measures scores of bell-shaped distribution with a mean of 100, standard deviation of 15. What percent of people have IQ scores between 70 and 100? So this is what requires us, because it's not a calculator activity. It requires us to label this, and some of you may remember this from Algebra 2. We're going to label the mean in the middle. Okay, so they tell us that the mean is 100. And the standard deviation, so the mean's 100, standard deviation is 15. So as I label each of the bottom dotted columns, I'm going to add 15 each time to label each of the bottoms. So 115, add another 15, gives me 130. Add another 15, that gives me 145. To label the left side, I got to subtract 15 each time. Subtract 15, I get 85. Subtract 15, I get 70. Subtract 15, I get 55. And then now it comes into play, me looking at the numbers they tell me to focus on and decide, okay, what zones are they talking about me adding up? Okay? So like on this first one, on part A, they said, what percent of the people are between 70 and 130? So that means I got to add the 13.5, the 34, the 34, the 13.5 all together. Now, I can do that, or I remember, technically the 70 and 130 represent how many deviations away? 2, technically, each way. There's 4 zones, but technically it's 2 deviations. So this is -2 deviation. That's +2. So I should know for this one that it's about 95%. Because 95% of the data is within 2 deviations. I can either do that with that part or add up all the individual zones. What percentage of the people have IQ scores less than 70? So I'm going to erase what we did here. Erase that. Less than 70, so 70 or less. And then or greater than 130. Well, that's the outside part. So I got two ways I can do this one. I can either take, okay, what's 2.35 plus 0.15 and multiply it by 2 because that's what the other side is. Well, that's 5. Or I can say, and this is where what we call the complement rule comes into play. Well, the two red areas or pink areas I'm highlighting is the opposite of what we just found. So I can technically do the complement rule, which is 1 minus the 95% zone, which is 5%. There's two ways to think about it. Again, if you don't want to, just add up the zones. 2.35 plus 0.15. On this side, you would add another 2.35 and another 0.15 is what you would add up. And then what percentage people has an IQ score greater than 130? All right. So that one, we just get to take off that portion. So that means on that problem, I'm just worried about not multiplying that outside 2 by 2. I just want what those two things added up to be. And that would be 2.5%. Again, the next several problems are just getting us to practice doing this. We have these on the problem in the assignment where you have to go through and do this. I would suggest creating a generic curve, label it, and then go from there. You can do it mentally, but again, sometimes we need to, work with the picture there. Eventually, as we transition this semester, they're going to give us numbers that are not the markers for the standard deviations. It's going to be between things. And that's where we use another process to get more exact. Because right now, we can roughly approximate this if they give us these numbers that end up being these little column headers as we look at labels. If they give us something that's not one of those, we can get a rough idea, but we can't get it exact and then that requires us to use a calculator method we learn a little bit later. As we go through here real quickly, we'll do this one together here. Then we'll probably go back. Oh, I definitely want to do that word problem. And then we'll talk about Chebyshev. SAT math scores have a bell-shaped distribution with 150 or 515 in the middle, and then a standard deviation of 114. So as I label, I'm going to add 114 to the right, and that gives me with 629. Add another 114, gives me 3. Carry the 1, 4. Carry the nothing, and that's a 743. Add another 114. And that gives me a 7, 5, 857. Did I do any of those wrong? I'm hoping I didn't. This one will be a little bit harder. Subtract there, that'd be a 1, and that'd be a 0, and that would be a 4. Ooh, that's going to stink on this one. Subtract those two things together. Ooh, that's a 3, and then that becomes a 9, and that's a 7 at the end. That's a 9 comes down. No, it doesn't. That's an 8. And then that's a 3, that's a 2. And subtract from that again, and that gives me 3, 7, 1. Did I do okay on the subtraction? Anybody doing it faster than me with the calculator? Subtracting 3-digit decimals are tough when you're not doing it by hand. Right now, it looks pretty good because I got some of the numbers that they're giving me up there. So, all right, so now part A, what percent of the SAT scores are between 401 and 629? All right, well, that's the two middle zones added together. That'd be 68%. What percent of the SAT scores are less than 401? So I go back and erase. And I say less than 401, so to the left of 401. And greater than 629. Again, you can add up all the zones, or I can basically use the complement rule, which is 1 minus the 68% zone. which gives me like 32%. And then the last one, as we erase, and I know I'm going fast. The last one, what percent of SAT scores are greater than 743? That's these two little zones here. That's 2.5, because again, it's 2.35 plus 0.15. Again, to me, it's helpful to memorize the zones when you get to use the empirical rule. We're hoping this is the last math course a lot of us have to take. So it's, hey, we just got a little bit longer of memorizing some useless information, if you want to call it. Get through the course and boom. Because most of us are not going to take a lot of math courses in college. This is the one and done. That's why you're doing it. You're trying to get your math credit. That way you can focus on your major stuff more. Because for a lot of your majors at your schools you're going to, this counts as that math credit. You don't have to do it again. Okay, so we got one more semester of just memorizing some things, and then we can purge it. Okay. Now, I will say it's handy in business world and other things when you're just trying to do a rough approximation of stuff, when you notice that it resembles a bell-shaped thing. But here's another example. So here's a word problem. So let's take that and then push it out and try to go through. Suppose Professor Alpha and Professor Omega each teach introductory biology. You need to decide which professor to take the class from, and you have completed your introductory statistics course. Records obtained from past students indicate that students in Professor Alpha, so I'm going to just write down Alpha here, Prof Alpha, have a mean score, so mu is equal to 80%, with a standard deviation of 5%, so fat R is equal to 5%, while Professor Omega, Prof Omega, had a mean score again, mu is 80, and a standard deviation of 10%. Decide which instructor to take for introductory biology using statistical arguments. So I'm going to draw a quick little, I can draw a quick little bell curve and just saying, okay, if it is approximately normal, and I draw my little bell curve, we would have 80, 85, 90, 95, and then, of course, there's the hundreds out there. Over here, we'd have 75, 70, 65. As I look at Professor Omega, yeah, the middle is 80, but then we have 90 and 100, and then we have 70 and 60, and then 50. We really can't label to the right on that one. So it's like, maybe the empirical rule is not a good way to decide who's, because, again, we don't have any data. Maybe we go back to the beginning part of the lesson. Maybe the empirical rule doesn't help us. We say, all right, they have the same mean, same mean, same mu. So let's take a look. Sorry, that's a crazy mu. Let's take a look at the standard deviation. We are comparing 5% for alpha, and omega was 10%. Who's got a greater spread? Who's got a greater variance? Which professor? Omega, don't they? Doesn't omega have a greater spread? So when we think about a greater spread, that means there's a greater range in scores. You can either score really high, but you can also score really low. Whereas when we look at a smaller spread of 5%, it's more consistent around the average. So there's more people scoring around that 85 to 75% with Professor Alpha compared to Professor Omega. Yeah, you might have the 95 and the 100 there, but then we also have the case of the 65 or 60, potential down there. All right, so To me, I would probably go off of Professor Alpha because there's less spread. I can be more guaranteed I'm going to be in this range of a score. I'm going to be really close to an 80%. There's very little variance away from that. Whereas with Professor Mega, there's great swings either way. Okay, and so my justification would be on the standpoint of Professor Alpha has a smaller standard deviation which means smaller variance his students or her, his or her, we don't know if it's a guy or girl, his or her students score consistently around the mean of 80%. Okay. He has more students, or her have more students scoring consistently around the mean of 80%. Okay, so that's my justification. Is granted I couldn't figure out with the empirical rule, so hey, I look at another statistical method. Let's look at just the variance. Who's got a smaller variance? That means their students are scoring more consistent to the mean. And I would rather, hey, know that I got a greater chance of scoring that 80% with that professor compared to, the other one. There may not be that great of a chance. Last little part here, and I know we're almost running out of time, but it's actually okay for Chebyshev because I did not put any problems on Chebyshev. I just wanted to show you. Chebyshev inequality can be used with any type of distribution, whether it is skewed or symmetrical. And basically, you have to determine, what your K value is. K has to be, greater than 1. And we can use this little formula of 1 minus 1 over K squared times 100%. And that will tell us what percent of the data are within certain parts. Again, there's nothing on the final practice exam that has this on there. I did not put any problems inside of the homework for you to do on Chebyshev. Not even sure if they gave us any options on the Pearson Online. But I did want to tell you that there is a way when it's not symmetrical, not bell-shaped, that you can still figure out what percent of the data is within so many deviations of the mean. And that's where this Chebyshev's inequality kind of comes into play. So another statistics course may use it a little bit more as they're analyzing skewed data more precisely. So